Well, good afternoon. Happy to be here. And as I'm talking about space, I thought I'm going to bring something out of space. Where are the Star Wars fans here? Anybody? Very good. So that's made out of DED. Any guesses? How long does it take to make such a part in DED? Any guesses? 20? 8? So as a matter of fact, it's 1 hour 15. If you would make it out of a powder bed, then it's around 10 hours, something like that. Every technology has its pros and cons, that's for sure. What I will talk to in my presentation is it's not an either or, it can also be an and. How we can combine powder bed and DED technology into one application and come up with new solutions for our customers. And I'm glad that I still see Star Wars fans smiling at this Mandalorian helmet here. So, a few words about MT Aerospace, where we originally come from. We were founded in 1969, so already some decades old. Typical small, medium-sized enterprise in the south of Germany, in Augsburg. We are part of the OHB group. That's one of the European leading satellite companies. And since the foundation, we've been working on highly stressed, complex components for the space and aerospace industry. I'm going to show you in a minute what that means. So that's where we originally come from. Since 1971, we are a core partner of the Ariane space program. And the space fans amongst you will know that there has been launch number 117 of the Ariane 5 in July this year. Hopefully, very soon there will be the launch of Ariane 6 next year. And we've been contributing around 10% work share in those rockets. And basically what we are doing is we are providing those huge tanks and structural elements for rockets for the Ariane program, but also beyond. We are also working with NASA, we are working with other American customers and also with Asian space programs. And just to give you a feeling, if you look at Ariane 6, that's the 10% work share. We are talking about those huge tank structures here. Just to give you a dimension here, they are 5.4 meter diameter, 20 meters long. So huge tanks which are emptied within 180 seconds. That's what's happening when you launch such a rocket like Ariane 6. And that's our traditional business. That's where we are coming from. And based on that history, legacy with Ariane 5, Ariane 6, we are now on a transition to further broaden our business scope, to go into new areas. And as we've been working with liquid hydrogen in those huge tank structures, it's quite a normal next step to also go into hydrogen electric propulsion systems. I will come to that in a second. But based also on that metallic expertise that we've built up, because those tank structures are welded initially, we have also set up our own additive manufacturing business unit. And that's basically the value proposition, that we are acting as an AM contract manufacturer. What does contract manufacturer mean? It's really covering the whole value chain, so we are able to consult our customers in terms of topology optimization, design, requirement engineering, but then also printing. And then what is equally important, also the post-processing, be it machining, depowdering, CT scanning, certification, qualification, all those things are also in scope. What we're doing at MT Aerospace, we are partnering together with EOS and AddUp. And most of the things that I will show now on the following slides can also be seen on their booth during the show. So we're not only active in space, aerospace, we're also doing serial production projects in defense, space, automotive, motorsports. So we go beyond space and aerospace. Today I will focus on what we do in space. And to start with powder bed, I brought two examples here. One is Rocket Factory Augsburg, if you will, and if everything turns out well, that will be kind of the European SpaceX. They are supposed to be the first private launcher. They will have the first rocket that goes into space second quarter next year. They have passed all their hot fire tests, and what we are doing there for Rocket Factory Augsburg, we are providing approximately 15 parts for their helix engines. You see here the rocket nozzle that can also be found on the EOS booth. You can also see it there. Much more, it's a very tricky part. It looks very boring actually from the outside, but with all the conformal cooling channels inside, it's a really tricky one. Even trickier is the nozzle injector that you can see here, which was originally assembled out of 248 of those small parts. All of them are now printed directly into one part. So that's one example for powder bed space, what we're doing at Rocket Factory Augsburg. I brought another example if we're talking about aerospace, and I said before hydrogen. So we are working with partners like Siemens, Fraunhofer, KIT and Leichtbau on next generation hydrogen electric propulsion systems for airplanes, where we are basically using liquid hydrogen, which is, as it says, liquid, then gaseous, and then we have heat exchangers, which then heat up the hydrogen to room temperature, so that at the end, a fuel cell and then also the engine can work with that propellant. So the heat exchanger is a very critical element in such a system. And we have worked on that in terms of designing such a heat exchanger, coming from the big picture, then breaking it down into requirements for the heat exchangers, also doing metal or material specimens in order to find out what are the minimum possible structures that can be done with additive manufacturing there. We have done CFD simulation in order to really make sure that those heat exchangers work in theory. But then we have also printed them, in this case on an AddUp Formup 350 machine. It's made out of titanium, grade 23. So we have manufactured it. You can imagine with all those very, very filigree structures that are inside such a heat exchanger, printing is one thing. The other challenge is, how do I get the powder out of there and make sure that there's no powder left? That's also something we tackled. That's also something that we mastered. And we also have done CT scanning on those parts in order to really make sure that there's no powder left in there, that there are no cracks. So the whole value chain, that's something that we covered for this heat exchanger. And what is now a final step in this project is we will set up a cryogenic test stand at MT Aerospace in order to really also test the heat exchanger and make sure that it's working as we saw it in the theoretical models. And then we take it to the next step. And if you listen to aerospace players, they are all talking about zero emission aerospace. Heat exchangers like that will be one crucial element in such propulsion systems. So that was about powder bed. Let's switch gears to DED. Again, there we have a very specific use case, satellite tanks. Those tanks initially were forged. They were sourced out of Russia. So already in the last decade, we had very long lead times, up to 12 months, to get those hemispheres. Now with the war in Ukraine, it's impossible. You don't get those hemispheres anymore. So there was a project that was set up with ESA in order to come up with 3D printed hemispheres that are then welded together into satellite tanks. And that's the challenge we took up. You see also the requirements. There are really tough requirements on such satellite tanks. And for that, we use then DED technology. You see here some examples. There are, again, pros and cons also for such a DED technology. It's what we have seen before, 1 hour building time versus 10 hours building time, so it's much, much faster. It has a different surface roughness, so it is rougher, but if you, the fans who want to touch the helmet here can see it's already a pretty good surface roughness that we can achieve with DED. The whole experience that powder bed has already in terms of process development and how to build parts, that's something that still is under development for DED. There's a lot of know-how in certain people's certain experts, but it still has to be brought into software that it gets more and more efficient. So we're working with a DED machine there. In this case, again, it's titanium what we're using here. We have 2 different lasers, and that's also important to mention, it's powder DED, it's not metal DED, it's powder DED what we do here. And that's the challenge we took up. We want to industrialize that process and make sure that at the end we can have satellite tanks at an industrial scale that fulfill the certification criteria that ESA has for parts that go into space. And for that, we set up at the end, it's an industrialization project that we set up there. So to qualify the powder, the machine setup, how to handle the data. We also put monitoring software in there in order to really make sure that we can go step by step and reach the different TRL levels and make this really an industrial approach. So with that, we also gathered a lot of data. So we have data on the mechanical properties, microstructures, thermography, NDI, all the different data that are necessary in order to, at the end, qualify and certify such satellite tanks for real industrial use. And where are we there right now? So we have achieved a TRL 5 level there. We are planning TRL 6 in first quarter of next year. Right now, what we can achieve with DED on a very stable basis is diameters up to 40 centimeters, so 400 millimeters. We want to go larger. And 1 meter diameter is something that is definitely in reach. That's also something that we see already on the horizon. That's not rocket science anymore. That's just the next step that we have to take there in order to get bigger. But then also to weld the hemispheres together, the machining to ensure then also the right surface roughness. Those are steps that we have on our timeline and that we will take next. But then we took it one step further. We said, why not combine powder bed and DED? And that's then the case, what you see here, very special satellite tanks, which are like ring-shaped. Those are tank structures which sooner or later will be part of moon landing missions. So either satellites, also spacecrafts, because they have a very good payload ratio. They also have very special geometrical conditions which are helpful for such missions. And that's the challenge we took up next. So our idea was, well, can't we combine powder bed and DED in order to really come up with those ring satellite structures? And that's what we did then. So what we have is, we have kind of a membrane in there that we call it the buffle. That is printed on powder bed, in this case again on an ADAP machine. And we use that then as a building plate for DED. And the hemispheres are then put on this building plate via DED. We have done that and prepared the whole job in Siemens NX. So we have also kind of a digital twin. We can simulate the process already in Siemens NX. We can set it up and then do the real-time production. And I also brought some videos here that you can see. Well, on the left hand, how does it look like in the simulation? How does this digital twin look like? And then also the the real-time DED production process, where we, what you can see here, built the DED hemisphere on the powder bed substrate. How does that look like then? This is what you can see here. To be honest, here the welding is still a tape. It's a green tape. So next step is that we do the welding, but you can already get a feeling if you put those two hemispheres together that you will then have those closed tanks. And then if you add one to the other at the end, come up with this ring-shaped tank structure. I mean, again, there we are not at the end. We are at TRL level 4 there. What we achieved right now, we will do now the pressure tests, surface finishing, and again, it's about scaling then to bigger diameters to come up with 1 meter tanks in diameter. This part, as you see it here, can be found on the Siemens booth. We partner up there, so the whole digital twin and everything in the software is done with via Siemens NX, and then the part is printed on the Beam Modulo 400 machine. So that's how we combine powder bed and DED and make the best out of both worlds. So it's definitely an and. It's not an either or. There are also applications out there that can be combined, where those two technologies can be combined. Well, to summarize, we invested heavily into setting up this AM business unit in order to also qualify different applications for the use in space, in aerospace, and then also other industries can benefit. But it's definitely an investment that companies have to take. But with that, we are set up to serve as AM contract manufacturer for space, aerospace, and other industries that I have shown you. Last not least, all those parts that I showed now can be found on the booth here at Formnext. So at the ADAP booth, that's just a level down here. EOS is just right at the corner. And the Siemens booth at Hall 12. There you can feel and touch and have more discussions about those parts. And I hope to see many of you there to answer further questions. If there are any further questions right now, happy to take them. And thank you very much for your attention.
Anybody with a pressing question that you'd like to ask now, rather than take it to one of the booths and ask it in secret? I always like to know, if you walked off the stage now and you're walking back to one of the booths, what is an innovation from this industry that you would like to see and think, oh, I've got to take this back. I need to buy one of these, or I need to tell my colleagues about this. Well, it could be anything,
yeah,
realistic or realistic.
And I've been with EOS before I joined MT Aerospace, so I think I can also put myself into those shoes. I mean, at the end, it's that's true for powder bed as well as DED. We have to together make sure that we get the right data and the data in order to certify and qualify the parts. Because that's at the end, that's going to be crucial, that we are able to convince customers and also to convince the certifying bodies that those technologies are reliable, that they are mature, and that engineers can work with that without any problems.
What do you see as the timeline for that, so that you can overcome those skepticisms and prove to the bodies that this is a real and viable set of processes?
Well, for the parts that I've shown here, we have achieved now TRL 6 level. So we're not talking about 5 years. We are rather talking 1 to 2 years.
Okay, perfect. Thank you very much.
Thank you.